Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. No, survey says you can either go up a full step on the ladder or not at all, right? That's the thing about a ladder. What the term we use is discrete. Discrete. That means that there are specific places where you can step up to, but you can't do half steps, or you can't do 3/4 steps. You can either do all of it or none of it at all. Okay? Or, for example, you could do 2 steps, right? You could go from the ground floor up to 2 steps, or up to 3. Okay? But you are not allowed to go half a step, or 1.5 steps, or 3/4 of a step. Those are not allowed. Okay? A ladder is a tricky thing. Good so far? Okay, so here we go, a little bit of chemistry. Okay? And here is the conceptualization that we're going to need. It's called the Bohr model. Now, if I asked you to conceptualize what an atom looks like, my guess is that immediately you're going to think about the Bohr model. Okay? The atom, you could conceptualize it, you can conceptualize it as a nucleus, a central portion containing the neutrons and protons, and running around the nucleus are electrons. Okay? So usually we think of the electrons as orbiting the nucleus. And I'll put nucleus in here for completeness. Okay. Okay. Now here's the thing I want you to be thinking about. Let's think about those orbits of the electrons as being the rungs on a ladder. Okay. What I mean by that is that an electron can move between rungs on a ladder. It is not allowed to move only part way. Good so far? Okay, good. So the question is, how can we use this idea? How can we use the idea that electrons are only allowed to go integer steps? Okay? So imagine for a moment that I have a couple of electrons and I have a couple ladder rungs. We'll call this the n equals 1, n equals 2, n equals 3. Okay? Well, the electron is no different. It is not allowed to climb a ladder rung unless it absorbs some energy. Okay? So in order to go up a ladder rung, the electron must absorb some energy. Well, how does it do that? We are going to give the electron energy by letting it absorb light. We'll take our electron ladder, we are going to shine light on it. Now notice this is supposed to be indicative of the white light. In other words, light that contains all of the wavelengths. Okay? And so what happens? Well, the electron needs a very specific amount of light to climb up a ladder rung. It is not allowed to take in everything, right? There are only specific wavelengths that correspond to the jumps to getting to the right ladder rung. And so if I take a full spectrum of wavelengths, I shine it on my electrons, one of those colors will get absorbed, whereas the rest will not. Okay, so I took out the red light. Because of that, if you're sitting on the backside and looking at what light is absorbed, you will get dark regions. These absorbed wavelengths correspond to the energy required to move the electron up a ladder rung, or 2 ladder rungs, or 3. Okay? Oh yeah, I should ask you, review question. Long wavelengths, down here where the red is. First of all, what's the wavelength of red light? Yeah, good. It's about 700 nanometers. Meters. So over in this range is like the 700s. Over here, yeah, 400. Okay. Next question. Okay. Which light is more energetic? Short wavelengths or long wavelengths? Good. Short wavelengths. So that means that this is high energy. And this side would be low energy. Good. Okay. Next question. Red light, low energy. Okay. Would that mean that the electron is jumping lots of ladder rungs, or is it jumping only like 1 ladder rung? Yeah, good. The jumps, the distance of the jumps, okay, is indicative of the energy. If you want to go 1 step on the ladder, that is going to require less energy than, say, if you want to go 10 steps up the ladder. Okay? So this would be like a single jump, right? Say from maybe the n equals 2 to the n equals 3 state, whereas this purple line that's missing might be from the n equals 1 to the n equals 3 state. Pretty cool, huh? Okay, good. Okay. Well, what about, you notice this is what we would call an absorption spectrum. Again, it's not by accident we name that. The electron absorbs the energy associated with those wavelengths in order to move up the ladder. Well, you say, wait a minute, Greg. Could the opposite process happen? And I say, yes, it could. Very good. You're extrapolating to the future. That's perfect. The opposite process can also happen. To fall from a higher ladder rung to a lower ladder rung, the electron must give off some energy. To go up the ladder rung, we fed the electron energy via light. To fall down, the electron is going to emit energy as light. And so it emits that color back. And so I've got here an emission spectrum. It's not by accident that for a given element, the absorption spectrum and the emission spectrum are going to look basically the same. Those lines are going to be located at the same wavelengths. It's just a matter of, is the electron going up the ladder and therefore needs to absorb the light? Or is it dropping down the ladder and therefore needs to give it back off? Pretty cool, right? There's one more piece that we need to take in order to get this all together. The periodic table. How do we organize the periodic table? You got it? Yeah, good. You're probably trying to remember some stuff that we learned in a science class at some point. I know you've all seen the periodic table. You probably landed on something like the periodic table is organized according to the number of protons in the nucleus. I will give you an alternative idea about how the periodic table is arranged. It's comparable. It's the same idea. It's just a little different way of phrasing it. I will say that the periodic table is arranged according to the electron ladders. What I mean by that is that each of these elements has a slightly different arrangement of ladder rungs. Helium, for example, has a different ladder rung spacing than hydrogen, which is different than lithium or beryllium. Each one of these elements has a different spacing of the ladder rungs. What this means? If we can get an idea about the absorption or emission features, we know that those are specific to a particular element. And so if we see a particular absorption feature, we can relate it to a particular element. The absorption spectra or the emission spectra serves as a fingerprint. We can identify the element based on the spectra. Boom, there is our composition idea. Pretty cool, right? Let me give you an example, okay? Here we go. The spectra of an unknown object and 4 elements are given. So our unknown object is up here at the top, and then I have given you the spectra, and we'll say that these are the emission spectra of 4 elements. Okay? So the white bar is to represent a wavelength that is being emitted. Okay? So here's the question. What is the composition of my unknown object? Go ahead, take a minute, see if you can come up with an answer. You got it? Yeah, good, good, good. And of course, one of the things that makes it a bit tricky is if you're dealing with an unknown object, you have no preconceptions of what it's comprised of. So all of these emission lines are going to be jumbled together, and you have to be able to tease them out almost one by one by one. Okay? So what I have to, usually how I try to do it, is I look at the unknown elements and I try to identify a line that is present for one of the elements that isn't present for the others. For example, let's take a look at this line. Look at this emission line in carbon, right? There are no other elements that even have a line close to that. But we see that our unknown object doesn't have that line either. Right? So carbon is definitely not contained in my unknown object. Okay? Well, let's go ahead. Let's take a look at the far side. Right here, you notice there's a line that's present for hydrogen, but it's absent for the other 3. Okay? Well, let's take a look at our unknown object. Ah, look at that. Ah, bingo. Right? We see that that lines up. So this object must have hydrogen in it. Okay? And so we say, okay, well, if that's the case, then the rest of the lines for hydrogen also must be present. And we see that indeed, that is the case. All 4 of the hydrogen emission lines are being exhibited by this unknown object. This unknown object must have hydrogen in it. Well, we got to keep going. Well, let's see here. We've already decided it definitely doesn't have carbon. Is there a line? Very easy. Okay, let's use oxygen. Now we see that oxygen and sodium, this spacing, sodium doesn't have that. Oxygen does. Let's see whether our unknown object has the same emission feature. Well, we go up and we see that indeed, yes, it has that line in there. So this must contain oxygen as well. Well, let's go through and take out all of the oxygen lines. Okay, yep, there's that. Okay, yeah, good. That's, okay, good, good, good. And we'll go ahead, yep. That one's taken care of, and yeah. Sweet. So you can almost conceptually think of removing those emission lines now from the figure. Well, are there any other lines being exhibited by my unknown object? No, they're all accounted for. Hydrogen, oxygen, 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 hydrogen, oxygen. Yep, they're all taken care of. So we now have what our object must be comprised of. It must be comprised of both oxygen and hydrogen. Okay? not sodium or carbon. Pretty cool, right? Yeah, okay. So here's one of the really cool historical applications of this. Go back to the 1850s. We are just discovering this idea that each element exhibits a unique set of emission lines. Incidentally, this is at a time that we don't even have a good conceptualization of the structure of an atom. In other words, we don't have the Bohr model. It's not for another 50 years that we get a good idea about protons, neutrons, and electrons. So this is pre-Bohr model, and we're discovering this emission feature. Now, astronomers, scientists, chemists, physicists, they start organizing the periodic table. And when there's an interesting thing, astronomers take this newfound technique of spectroscopy and they record the solar spectrum. They record light, they divide from the sun, they divide it into its corresponding wavelengths. And there's a very interesting thing. They identify a very strong yellow line that they cannot associate with any of the known elements. And so astronomers say, well, maybe there is an element on the sun, in the sun, which we have not yet found on the Earth. That element must be responsible for this unique yellow emission line. And so astronomers say, well, we will name this element blank after the sun. What's the element? Yeah. What word, what suffix have we used to describe the sun so far in this class? Yeah, you remember heliocentric, helio referring to sun, and then centric, centered. So that suffix of helio is something that we use to describe the sun. This unknown element that astronomers discovered applying spectroscopy to the sun, they named that element helium. Helium was first discovered not here on Earth, but was hypothesized to exist based on the solar spectrum. It wasn't for another 10 or 15 years that scientists were able to actually collect and purify helium in order to obtain the spectrum. Okay, so I think that's it for this discussion, but keep mulling that over. But this is how we can use light to infer the composition of objects. No longer do we have to actually go and take a ladle of the sun and take it back to Earth and analyze it to figure out what the sun is made out of. Similarly, we don't have to land on the surface of a planet in order to figure out what the planet's made out of. We just have to get a good recording of the spectrum. Okay, well, I think that's enough for this lecture. I thank you for your attention. Keep up the good work. I'll see you next time.